JJ solve the exercises that he gave you in the slides together with you. So then Valerio will be tutoring us today and then on Wednesday. So there will be a decrease in tension.
Okay. Yeah, as Giuseppe said, I'm going to propose some exercise today and the next tutoring in 2 days. So it will be that you have to do the work using your laptop. So I think I will not propose something to do on the paper, but you have to use your laptop. And I'm going to propose something using a Jupyter notebook. I don't know if you have experience with that. It's not that you have to do with the Jupyter notebook. You can do with whatever software you prefer, but I prepared a tutorial with a Jupyter notebook. I have 3 slides explaining something that Riccardo already explained this morning. After these 3 slides, I'm starting to explain what I'm giving to you. I'm giving to you data and also what I'm asking as exercise. So I think we have 2 hours. Maybe, I don't know, I have these 3 slides and then we start to do some practical work. So I think during these 2 hours, we try to do the exercises. So we are talking about germanium detector that I usually refer as high purity germanium detector. Ricardo talked 2 hours about this kind of detector. This is what we use in Legend 200, and what was used in other experiments like Gerda and others. Here you can see a picture of one germanium detector used in Gerda and also used in Legend 200. So it's something more or less of the size of, this is a coaxial detector, also called semi-coaxial, of the height of 10 centimeter and diameter also of 8, 10 centimeter, something like that. You know how a germanium detector is working. Basically, the detector are based on this PN junction. So you have one part that is doped as P-type and another doped as N-type. And basically, we are able to have an active region that is more or less of the same size of the germanium itself by reverse biasing this PN junction. So this is the working principle in few words of a germanium detector. So basically we use an high voltage of the order of the kilovolt to have the so-called depletion region more or less of the size of the germanium itself. To give an idea of what of some number that I think is always important as experimentalist, I just wrote here an example. So this is a factor that Ricardo already showed this morning. This is the average energy to produce one electron hole pair, that is 2.96 electron volt. So if you have a release of 2.96 electron volt, you have n equal to, you have one pair electron hole. So if you have one event inside the germanium of 1 MeV of energy, and if you do the calculation with this simple formula, you get this number of events, of pairs. So you get 3 times 10 to 5 pairs in your germanium. That is quite a lot, let's say, and this is connected to the fact that this kind of detector have an high resolution. So this is one of the most important characteristic of this kind of detector. The resolution, I also wrote here, the resolution of this kind of detector is really good compared to other types of ionizing detector because of this factor here. So this factor is really low and you get lot of electron hole pairs. If you convert this number in charge, you get this 54 femtocoulomb. So this means that you have an energy of this size that is more or less the energy range where we are interested for the double beta. you get this small charge of 54 femtocoulomb. You can do the conversion just by using this simple formula. I don't know if you have some question on this already. Otherwise, I move to what? Yes. No, sorry. Can you repeat the question? No, I think the N type is doped with lithium. Is
N-type and P-type.
okay.
It's just notation.
Yeah. It's just it's not a minus. Okay, if this was the question. Okay, I move to this part that is more connected to what I'm proposing. In this slide, I'm trying to explain how we pass from the signal that is produced by the detector to the data that I'm giving to you. So basically, the detector usually are read out by, let's say, an electronics circuit that is usually called charge-sensitive preamplifier, that basically is shown here. This is a very simple, this is a sketch of a preamplifier. In reality, it's more difficult than this. Basically, you have an amplifier with a so-called feedback circuit with a capacitor and a resistor. Basically, what from the detector you get a fast signal, usually, let's say a fast signal, I don't know, this is a sketch of how a signal can look like. And then you integrate by using this capacitor, this feedback capacitor. And then the resistor is basically restoring the voltage to the initial level. So usually a signal, if you read out the signal at the output of this circuit, you get something like this. So basically you have a flat part before the event, then you have a sharp increase, and then you have an exponential decay. So basically this, I'm just also writing how the three different parts are called in our, let's say, language. This is the baseline that, as I said, is flat. Then we have this is usually referred as rising edge or leading edge, that usually for us, this has a duration of 40 to 100 nanoseconds. And then we have this exponential decay. The exponential decay is slower, as you can see from this plot here, is of the order of a few hundred of microseconds. But this decay time depends on what you are using as a resistor and capacitor in this system. I'm writing you the example of the values that are used now in the circuit used in Legend 200 with a resistor of 1 gigaohm and a capacitor of 0.4 picofarad. You get this tau. If you do the calculation, if you multiply R times C, you get 400 microseconds. That is the decay of this signal here. I also I converted this value in voltage. That is what we are measuring. So with the signal, with 1 MeV of energy, you get this charge. You get 54 femtocoulomb of charge. And if you convert this charge in voltage by using this capacitor, you have this voltage. You have 135 millivolt. That is basically the amplitude of this signal here. So we have voltage, but let's say to save our data, what we do, we convert the analog signal in a digital signal that then we save in our computer. And this is done by what is called an analog to digital converter, that I think is something used in all fields that are acquiring signal from a detector. In Legend 200, just to give you some specification for the ADC, in Legend 200 we use, this is relevant in particular, the sampling rate for the data I will provide to you. The sampling rate in Legend 200 is 62.5 megahertz. That means that 1 bit in time is 16 nanoseconds. If you do the reverse of this number here, you get 16 nanoseconds. When you will open the data that I will provide to you, you will see we will see also later. I will show you my notebook that one sample has the duration of 16 nanoseconds. I'm not entering in more details. I don't know if you want to ask. Yes.
So this is basically an integrated circuit, but
yes. This is. I think I think the amplitude is proportional to the integral. Yes, you're right. Yes.
So your signal, the input to the vector is not a current input, just a voltage.
No, it's a current.
You don't need a amplifier.
Yeah, I think yes. No, you don't need this. So it's actually what you do. Yeah, usually. Okay, no other question. So I have the third slides that I don't remember. Okay. So and then what we do with this kind of signal. So after you convert the signal in a digital signal, we save on our data. And what we usually do, we do this digital signal processing that is usually you take the waveforms or signals. We can call either waveforms, signals, raw signals, and you want to process in some way to extract the information of interest of your case, and you do this with the digital signal processing. There are many types of digital signal processing. Usually what is done is a discrete convolution of the signal with a filter, usually called filter. I'm just showing you two examples of filter. The trapezoidal is used largely in our field, but also another used filter is a cusp. The cusp filter that is looking like the green one in this plot here, while the orange one is showing you the trapezoidal filter. So basically, we take the raw signal, we perform a convolution with this kind of formula is the convolution, and you get a filtered signal. So the filtering is needed to reduce the noise, and then you extract the energy. Basically, this is an example here. I will show also later when I will show the notebook. So you have your signal, you process in some way. The most simple, one of the most basic filtering is the so-called moving average, when you basically you average a subset of points together, and you get you do this in all your signal. But as I said, there are many types of DSP methods, but usually what we do is by using the convolution. So I will show later an example of this when I will switch to the notebook I prepared. Yeah, I don't know. Okay, I think so if you go to this is what I'm proposing you today. So I will provide to you the files, some file in a format, and I will propose to you to do an energy calibration. So I will provide an energy spectrum that is showing like this. I will provide not the spectrum, but the list of the energies. This is how the histogram of the energies looks like. So I will give you the list of the energies in this format. I will provide you the energies in this format. I will show you how to you open this kind of format, but I'm also providing you the a file that is in a txt format, so in principle you can open with I don't know, C++, MATLAB, whatever are you. If you are not using Python, you can also open the txt. If you go to the shared folder, I don't know if you have the link of this folder. And if you enter in my folder, D'Andrea, in data you will find the txt data and the LH5 data. So basically some around 4 megabyte, 3 megabyte, so I think you can easily download. And then in the main folder you can find the slides. The slides that are this PDF here, the Jupyter notebook, and this other file that you need later. So basically, I think it's nothing too heavy. So it's 1 megabyte, and the data are around 4 megabyte each file. In this slide, so if you open the PDF, or I don't know if probably this PDF has been added also in the main GGI event page. I think, no, probably Alessio already, okay, I don't know. If in any case you have the PDF in the shared folder, I also included the raw waveform. So basically, I'm calling the data in for level. This tier 1 data means the basic level, so the raw waveform, so the signal. For each event, you have one signal, like the one I showed you before, like this, basically. And it was not possible to put this file in the shared folder, so because it's a big file, it's 1 gigabyte file for each detector. I added the files for 2 detectors. But if you click on this link, you can download the 2 files. So it's something like 1 gigabyte per file, are 2 files in total. This file here, the tier 1, you don't need for the calibration, at least to do the first 2 steps here, because in the tier 2 data, you can find the uncalibrated energy. So basically, you find the list with the energies, and the tier 2 is in the shared folder. It's something like, as I said, 3-4 megabytes. Because to let you understand why this is so small is because for each event, for the tier 1, you have the entire signal, all the signals, so many points. While for the tier 2, for each event, you have 1 value. So this is, I think, quite easy to understand why this file is so small. I think you have in total around 300,000-400,000 of events. Then I will open you the Jupyter notebook that is including the tutorial that I think you can already download. Okay, I don't know if I'm already entering in too many details. No. Okay, so I'm just showing you what I'm asking you to do. I'm proposing 3 tasks. This is the first one. The first one is to perform the energy calibration by starting from the array of the energies, of uncalibrated energy. You can open the LH5 file. In the notebook is showed how to open, or you can use the txt. The txt is simply a list of values. You can open, I don't know, if you're not using Python, or also if you are using Python, you can open. So basically, you have to produce the uncalibrated spectrum, that is this. Uncalibrated values are in unit of ADC, so it's something going from 0 to 18,000. as you will see when you plot the uncalibrated spectrum, you will find the peaks. These are corresponding to 7 gamma lines that are at the energy that I'm writing here. So in Legend 200, we calibrate using this source, that is the thorium 228 calibration source that is giving you this, that is decaying. So basically what we do weekly in our detector, we move more than one calibration source close to the detector in order to have to perform the calibration. So basically, since we are looking for an event that is at around 2 MeV of energy, the neutrinoless double beta decay is at 2 MeV of energy. So we use this calibration source. One reason is because it's covering our range of interest, because the highest peak is at 2.6 MeV. So you are able to calibrate precisely at the energy where you are searching for your event. And this is why this is a good calibration source for us. There is also some other reason that maybe I will say you in the next during the next tutoring. So basically, you can produce this uncalibrated spectrum easily, and then you need some method to find for your peaks in your spectrum. So basically, you need to run some routine or some method to search for these peaks, only the one that I'm indicating here. For example, you don't have to search for this one, that is another peak, or this one that is another peak. And also you don't have to search for this one, also if it's probably the most intense peak in our spectrum, because this is coming from something different. This is not coming from the decay of this source, but this is something that we usually call pulsar. So basically we inject an electronic signal in our system around 1 MeV of energy, more or less, but we cannot use this for calibration because we don't know precisely which energy is. We know we inject this pulsar at a precise voltage, but we don't need the precise energy at the output of our detector, while we know the energies of the others, because we are able to recognize the shape we expect from these sources. In particular, the last one is clear, and then you can recognize the other peaks. Okay, so you need, as I said, to find some method to search for peaks and calculate the position of each peak in the uncalibrated spectrum. And the third point is calculate the calibration curve. That in the example I'm showing you later is a linear calibration curve. So for task 1, so you need to find the 6 peaks. I don't know. Oh no, they are 7. Okay, so in this plot I missed one. I don't know which one, but is compared to this, I'm not including one. So I'm sorry for this. So basically, you need to find the 7 peaks, and you need to calculate the position of each peak. In this example here, I performed a Gaussian fit of the peak because the peaks are all Gaussian peaks, and you need to extract the position. So basically, after you calculated the position of each peak, you have 6 or 7 points, and then you can extract your calibration curve. So basically, this is a plot of the energy in ADC versus the energy in KV. So basically, the calibration curve is something that is able to convert the energy from ADC in KEV. So probably you would expect this in the opposite order with the ADC in the horizontal axis, vice versa, but at the end is the same. So at the end, you want to have a calibration curve that is providing you the function to go from energy uncalibrated in energy calibrated. And then you can get the calibrated spectrum that is something like this, very similar to the other one, but with the calibrated energy. Like this is the 2.6 MeV peak that is exactly at 2.6 now. Okay, I think we can go to this later. So now I'm showing you the Jupyter notebook. I think you all are able to see this folder, right? Okay, I'm opening now this, the notebook. Okay. You can see. Okay, so if you're familiar with the Jupyter notebook, in the first, I'm just importing some basic, I don't know, NumPy, I don't know, the matplotlib that is usually used for plots, something very common. Then, if you want to use the Legend software, that is not mandatory, you need to install this software simply by using pip install pygama. The Legend software is called pygama. So if you run this command, you can use the Legend software. Is something public, is open source. You can go to these links to learn more about the software. You can install all the software by simply doing this. So you don't need to install separately these three things, but you can run this command. Basically, as I said, it's not mandatory, but I'm just, maybe you can learn how the Legend software is working. So to open the file, you need to import this LH5 module. That is also the format of our file. As I said, we have two detectors. One is called B0032B, and the other one is called V021, etc. One is a BG detector. I think Riccardo mentioned that we are using different types of detector. One is a BJ type and another one is an AC type, but for you, for this exercise, it doesn't matter which kind of detector is. So I'm just in the file name, there is the name of the detector. You can see, basically, this is, I'm opening, with this command, I'm opening the detector B00, etc. by using this command. With this command that you find here in this notebook, I'm opening only 100 events, not all, because the raw file is, as I said, is very large, so also you need some few seconds to open. You don't need the tier 1 to do the calibration, okay? The tier 1 is the file with raw signals. As alternative, also in Python, you can, instead of using the Legend software, you can use the H5PI package that is something, let's say, more commonly used in Python. That is basically the format of our data, that is LH5, is a modified version of the H5 that is a common format in Python in general. We add the L, where L stays for Legend, so is our custom format, but is not so far from the standard H5. In any case, you can open also the LH5 by using this package here. So it's up to you if you want to install the Legend software or if you want to use this. Or the other alternative, as I said, is to work with the TXT that I'm also adding here, and forget about Python and all that is written in this tutorial. I think as you prefer. Okay, before showing you the details of the calibration, I'm just showing you some how to plot the waveforms from the tier 1. So if you open the raw file, the raw file is containing this. Can you see the content of the raw file? This is the detector. So basically, in this tier 1 file are stored two types of waveform. One is what we call presummed, and another one is what we call windowed. So basically, we prefer to not save the entire waveform, but we split into waveforms that are that this is in order to save some space. And now I'm showing you both the two waveform. First of all, I'm showing you what is called the presummed. This is the presummed. The presummed waveform is basically long 130 microseconds, but you can see easily that the bins, I think let's say this DT is the sampling time. So the duration of one sampling is not 16 nanoseconds, but is higher, because what we do in the presummed waveform, we sum 8 samples together, and instead of having instead of using the full space of the original waveform, we get something of the same duration, but basically with less points. So basically the time resolution of this kind of signal is lower than the original waveform. And then we have the other one. I'm showing you the other one. The other one is shorter, is a shorter waveform. You can see it's only 22 microseconds, but is keeping the original sampling. So basically, we don't save the original waveform. The original waveform is 8,192 points with 16 nanoseconds of resolution, but we prefer to save two signals. One presummed, so basically not with 8,000 points, but with around 1,000 points, with less resolution, with less time resolution. And the second one is keeping the resolution, but is shorter. This is what we do, as I say, for saving disk space. So we don't keep the original waveform, but we split into shorter waveforms. So okay, I don't know if. Okay, so let's go to the energy calibration now, okay? So for the energy calibration, you need to open what I'm calling tier 2 data. If you open one tier 2 data with the Legend software with each LH5 routine, for this detector, for example, you can see that I saved 3 array. For each of the two detector, I'm saving 3 arrays. This we need the next tutoring. This probably we don't need. I don't remember why I saved this in the data that I provide to you. You need the third one. You need this trap Emax. So that is basically the uncalibrated energy extracted by using this trapezoidal filter. Okay? This is just showing the content of the data. Then you need to open. To open the uncalibrated energy, you can use this command here. Basically, I'm opening the trap Emax array with a simple command, and I use this point NDA to convert in NumPy array. and then I plotted the histogram. I think this is the last thing of this tutorial. Perfect. So I think if you are familiar with Python, this is a very simple command to plot an histogram. That is actually what I copied to the slides, this uncalibrated spectrum. You can also find that I wrote some instruction to in the notebook. That is basically what I explained to you, what you need to do to calibrate. Define the peaks, the calibration curves, search for peaks, etc. I did this by using the Pygama routines. Pygama is the legend software. But you can do, if you want to look at Pygama, is okay, but I'm suggesting you to do with some more basic Python package. For example, but this is not mandatory, it's just a suggestion, use the function find peaks to search for peaks in the spectrum. I'm also adding the link to where you can see the information of these find peaks. Curve fit to fit the peaks. I think curve fit is probably the most easiest routine to perform the fits. And then I also suggesting to use this polyfit to find the calibration curve. Okay, so that's it. I think this is the end of the notebook. Okay. So I think you can, if you haven't already started, you can start. So you can download the files, etc. Okay. So if you have some problem with, I don't know, opening files, other things, please ask. With Windows, so what you use the? No, I think there is no. At the moment there is no. No, I'm sorry for that. So I use Windows actually, but I use this. No, I think I'm using this terminal that is called the Linux subsystem. It's not a virtual machine, it's just a terminal that is like a Linux terminal. Okay, so maybe you can use this. Okay. Yes. I think I'm using the last one. I think probably I'm using but this probably is not. I'm probably using the unstable one, but should not matter so much. I hope. What you don't have? Sorry, this command, the. And how is called in your case? Which version are you using? A really old one? So this is installed since 1 year or something like that? No, I don't know. So I mean, if you have already experience with the legend, you can open with something else. No. No, this is something more recent. I think if you install the 2.0, I'm sure that this command is present.